Okay, so picking back up here, we were working on our Lewis structure for carbon dioxide. And we determined that carbon, being less electronegative, belongs in the middle of the skeletal structure. So we should next calculate how many valence electrons are present in the molecule. So looking at the periodic table, carbon brings 4 valence electrons, each oxygen brings 6. So that would be a total of 16 total valence electrons for our molecule. Now, we actually made 2 bonds because we have 3 atoms. We need 2 bonds to hold them together. That would be 4 total electrons that we've already used. So there's only 12 of the remaining 16 left. Now, this would, once we have the electrons and the skeletal structure, we can move to number 3, complete the octets of the surrounding atoms using the remaining electrons. Don't put electrons on the central atom until all peripheral atoms have complete octets. So we don't want to put any of these electrons on carbon at this point of the structure. Since we have 12 left, they should all go on the oxygens. Right? And this is something you always want to think about. We want to fill electrons on the outside or the periphery of a structure and share them toward the middle. We've already established we're putting the best sharer in the middle. So lower electronegativity means better at sharing, right? We'll actually see with formal charges about how we can predict how many bonds something is going to make. Right? The lower the electronegativity, the more likely an atom is to make more bonds as well. So those electrons should start on the outside and we share them in. You can fall into traps. If you put electrons on the central atom, you may not be able to move them to a place that gets you to the right structure. If you start on the outside, share in when necessary, you will always get to the right structure if you follow the rules. Okay, now get all the electrons in there and make sure you stop. When you run out of electrons, you have to stop adding electrons. What sometimes happens is a student will just keep adding more electrons until they've established an octet on every atom. You cannot do that. 4 extra electrons here, but it would take 4 more electrons here to put the octet on carbon. That is not carbon dioxide anymore. That is a ion, right? And then, in fact, if you added 4 electrons, that would be an ion with a -4 charge. That is not particularly likely to be stable, right, for 1 carbon and 2 oxygen. So make sure you stop when you hit this count. Okay? From there, right, we move to the last step. After completing steps 1 through 3, right, we want to try to share electrons to finish off the structure by giving the octet now to the central atom. So I'm going to start to color code here a little bit. I'm going to use some different colors to identify some different possibilities. There are actually 2 options here now for this structure. One will satisfy the people who like the idea of things being symmetric, right? 8 electrons on the oxygens, 4 on the carbon. That means we need to share to put 4 more on the carbon. One way to do that would be by sharing 1 pair from each side. That would give us this structure. Double bond between the carbon and each oxygen, and that would leave 4 electrons on each oxygen. And we've satisfied the octet rule, 8, 8, 8 on all of the atoms. But we have another possibility here. What if, instead of sharing 1 from each side, we shared 2 from one side? So let me redraw the skeleton we were using here. At that stage of the process, what if I did this instead? I share 2 from the left side here instead of 1 from the left, 1 from the right. That would give me this structure. Triple bond between that oxygen and the carbon. Single bond between the carbon and the other oxygen. Still 6 non-bonding electrons, the oxygen on the right, only 2 left, oxygen on the left. Now, that also satisfies the octet rule. There's 6 electrons here on this oxygen, 2, 3, 2, 4, 6, 8. Right? There's 8 electrons on the carbon, 2, 4, 6, 8. And there's 8 electrons on this oxygen, 2, 4, 6, 8. Now, one of these is a good representation of the bonding. One of them isn't. The octet rule is not enough for us to figure out which one is the correct structure. So we've got to look at some additional source of information. Now, if we look back at the original note handout, right, I have drawing structures handout there. We've been kind of jumping back and forth to that consistently. The last thing down here at the bottom is the formal charge. Now, in the middle of the worksheet, there is a definition of formal charge. So since you have the worksheet, I'm not going to write the whole thing out here, but let's talk about it for a second. Formal charge is the electrical charge difference between the valence electrons in an isolated atom and the number of electrons assigned to that atom in a Lewis structure. So the formula will be helpful here, right? And I'm using FC here as formal charge. This is something we could use to evaluate how well our structure represents what an atom should look like in terms of being stable in a structure. The formal charge can be calculated by taking the number of valence electrons, right, that particular atom would have. So that comes from the periodic table. So we find a carbon in a structure, it should have 4 valence electrons, or at least start the calculation with 4 valence electrons. Oxygen in a structure, start the thing with 6 valence electrons. Okay? From the number of valence electrons, we're going to subtract the number of bonds that the atom has in the structure we're looking at. Okay? So we drew a structure, we can count up how many bonds did we connect to that particular atom. And then we're also going to subtract the number of non-bonding electrons on that atom. Just that atom, not for the whole molecule, just the atom that we're calculating. Okay? Ideally, this comes out to be 0. That is the best representation of a structure for that atom, is if this comes out to be 0. It is certainly possible that we'll see a -1 here and there, particularly in an anion. If there's an overall negative charge, we'll have to have some negative formal charges somewhere in the molecule. We might see a +1 occasionally, but those can be a representation to us of less than ideal structure, which would mean potential reactivity in a molecule. Okay, now this formula is kind of written out in the notes, so I did abbreviate here as I described it, but if you look on those notes, this gives you a good indication. A couple other things, and these are in the handout as well. The sum of the formal charges on atoms must equal the charge on the molecule. That means if we have a neutral molecule, we find a negative somewhere, there should also be a positive. If we don't find that, there may be something amiss with our particular structure. And then the last thing kind of tells us how we're going to use this. A structure is the most stable when it has the lowest number and lowest magnitude of formal charges. Okay? When a formal charge is necessary, a negative charge will usually reside on the most electronegative element, a positive charge on the least electronegative element. Okay? Now, we're going to talk more about that, but let's see if we can finish our evaluation of carbon dioxide here before we have to switch to another video. So let me start with the one on the right, the one that I drew first. And I'm just going to use a little arrow here. And I'm going to use this formula, right? So I'm going to calculate the formal charge on that oxygen. Oxygen starts with 6 valence electrons. In my structure, it has 2 bonds. And in my structure, it has 4 non-bonding electrons. So that's 0. That's good. 0 is the best result for formal charge, would be the most stable way to represent that particular atom. So that oxygen is in good shape. Now notice, this oxygen, on the other side, has the exact same bonding arrangement. 2 bonds, 4 non-bonding electrons. The calculation would be exactly the same, right? And that's something to keep in mind. Once you get the hang of calculating formal charge, you shouldn't have to be plugging these into the equation all the time, because you'll start to recognize there's a specific way an oxygen is going to look in a structure, and then there are some other ways that aren't as good for oxygen, etc. And we'll talk about that in primarily in the next video. I kind of drew myself into a corner here, but let's say this carbon, right, the formal charge there, carbon has 4 valence electrons to start with. In my picture, it has 4 bonds, and it has 0 non-bonding electrons. That is also a good drawing for a carbon. So right there, those are all 0. That seems like our best structure for carbon dioxide because of that. If everybody's got a 0 formal charge, that's good. But let's see maybe where we can identify this structure as not so great. Looking at the carbon first, 4 valence electrons for carbon. There's 4 bonds there, -4, no non-bonding electrons. Well, that's still a fine looking carbon in terms of what we want in a structure. But let's look at the oxygens. This oxygen on the right of the structure. So oxygen starts with 6 valence electrons. In this structure, we drew 3 bonds to the oxygen, and there are 2 non-bonding electrons. 6 minus 3 minus 2 is +1. There's a +1 formal charge on that oxygen, right? That's not as good as a 0 formal charge. It might be possible, but it's not good. Often those will be indicated by drawing a little charge near the atom in the structure. I like to put a circle around the charge so that it's a little easier to tell what it is, right? A dash can kind of be mistaken for just taking a little longer to draw an electron. So I put a circle around there. You won't always see the circle, but just so you know what I'm doing. On the other side here, this oxygen, again, oxygen starts with 6 valence electrons. That's kind of what we're comparing to. There's 1 bond, and there's 3 lone pairs, which would be 6 total non-bonding electrons. The oxygen on this side has a negative formal charge, right? Or -1 formal charge. That is an indication that this structure would not have the same stability as this structure. If we could really build this structure, right, if we had little tweezers to grab atoms and electrons and move everything around, as soon as you let this go, the electrons would shift. And they would shift to turn into this structure where things are more stable. So this is the structure we want for carbon dioxide, right? And that's something we want to think about as we start to look at other structures is, do we have formal charges, and what are they? That's going to be a very important thing to recognize, not only when a structure is correct or is a good representation of bonding, but also it can help us identify reactivity, right, and how molecules are likely to react, which is something that'll be useful as well. Okay, we'll stop there. We'll come back. We'll talk about formal charges more in general, but then we'll move on with the additional structures.